welcome to the Deep Dive. Today we're taking you on a journey into a highly unusual, very visually driven source.
Yeah, it's definitely not your standard physics textbook, that's for sure.
Right, it's actually a translated blog post from an author who goes by Zionad 2023. And the title is quite a mouthful. It's Draft, Einstein Slacking 131 Blueprint. Let's notice the trick from the Design Space Blender.
Which really sets the tone, it's eccentric, it's deeply analytical, and what's wild is that the author uses a 3D animation software blender to actually visualize and critique the foundations of Einstein's special relativity.
And the Michelson-Morley experiment too, right?
Exactly. They basically use this 3D modeling program to expose what they claim is a mathematical trick or a patch in modern physics.
Okay, let's unpack this, because the premise here is just fascinating. What if we could use 3D software to map out exactly how light travels, frame by frame, instead of just relying on abstract equations on chalkboard?
And that is what makes this source so unique. It completely forces us to shift from a mathematical God's eye view to a physical camera eye view.
Okay, we definitely need to break that down for the listener, because to really get this critique of relativity, we have to build the design space they created in Blender.
Right, so picture this. The author models a cube. It's 20 by 20 by 20 units.
Like a perfectly symmetrical room.
Exactly. And they place the center of this cube dead zero on the grid, coordinates 0, 0, 0. And this cube basically represents a train carriage, or the inside of an interferometer.
An interferometer being the device they use to measure light interference, right?
Yeah. Now, here is where the core philosophical difference comes in. The author talks about the mathematical eye, which is that God's eye view we mentioned.
The idea that the math sees everything all at once.
Precisely. The mathematical eye sees all points in a 3D Cartesian space, your X, Y, and Z axes, as existing simultaneously. It knows where everything is right now.
But reality doesn't actually work like that, does it? Because we have to wait for light to reach us to actually see anything.
Right, and that's the camera eye. The author places a physical camera at specific coordinates, like x equals 0, y equals negative 40, and z equals 20.
Okay, so off to the side and a bit above our cube.
Yeah, and this camera eye only perceives things when light rays, which are moving at a speed of exactly 1 unit per second in this model, actually arrive at the lens.
So if I'm understanding this, it's like a video game. I mean, the game's code knows exactly where every enemy is at all times. That's the God's eye. But your character only sees them when they enter your field of view on the screen, the camera eye. The author is saying physics often confuses the two.
That is exactly the analogy to use here. The author believes confusing these two perspectives, the absolute mathematical map and the delayed rendered reality, leads to fundamental errors in how we understand time and space.
Because things that happen at different times might actually reach the camera at the exact same moment.
Exactly. If you put a transparent sphere around the camera lens, light rays that leave different parts of that 20 by 20 by 20 cube at totally different times will hit the sphere simultaneously.
Wow, okay. So the absolute reality and the observed reality are not always matching up.
No, they aren't. And to really test this out, the author takes our Blender cube and puts it in motion.
Right, the classic physics thought experiment.
Yeah.
The moving train.
You've got it. The cube is now a train moving through an electromagnetic field along the x-axis, and it's moving fast, like 0.6 C.
So 60% the speed of light. That is a very fast train.
Incredibly fast. And the author brings in some historical context here to ground things. They talk about Ole Rummer, who assumed the sun was at a 0 velocity in the electromagnetic field to measure light speed.
And James Bradley, right, with the starlight.
Yes. Bradley observed starlight falling vertically at exactly 1.0 C, but because the Earth was moving horizontally underneath it, it created an apparent velocity.
Oh, it's like, okay, think about driving a car through a heavy rainstorm. If you're parked, the rain is just falling straight down. But if you're driving forward at 60 miles an hour, the rain looks like it's slamming into your windshield at an angle.
Perfect example. The movement of the car changes the apparent speed and angle of the rain. Now, take that rain analogy and apply it to the light inside our train moving at 60% light speed.
Okay, here's where it gets really interesting. Because if you're inside the train, things get weird.
Very weird, because the apparent speed of light changes depending on which direction you shine it.
Right, because if you shine a flashlight forward along the x-axis, The train is moving in that exact same direction at 0.6 c.
So the apparent speed of the light closing the gap to the front wall is only 0.4 c, just 1 minus 0.6.
But if you shine it sideways, toward the side windows along the wire z-axis, it's totally different. The source says it's 0.8 c, right?
Yeah, that's just basic Pythagoras. 1 squared minus 0.6 squared gives you 0.8 squared. So laterally, the apparent speed of light is much faster than it is forward.
Which is incredibly counterintuitive.
Right.
Because if you, as a passenger, are standing inside that train, you think the light from your flashlight is moving uniformly in all directions.
But from the perspective of the outside field, the absolute geometric reality, it's completely skewed. And the author claims that this is where the famous Michelson interferometer experiment of 1881 made a fatal assumption.
Wait, 1881, wasn't it the Michelson-Morley experiment?
The author's very specific about this. They point out that 1881 was Michelson alone. Morley didn't actually join until the re-experiment in 1887.
Ah, okay. So what was Michelson's fatal assumption, according to the Blender model?
Michelson allegedly designed his first experiment thinking the light inside the moving device would behave exactly as if the device was totally stationary, like it had a zero velocity in the electromagnetic field.
He assumed the inside of the moving train was a closed, perfectly normal system.
Exactly. And the author asks us to visualize throwing photon balls inside this fast-moving train to prove Michelson's illusion.
Photon balls. Okay, I like that.
Yeah.
Let's say you throw a normal physical baseball inside a moving subway train. Classical mechanics says it moves completely normally relative to the train, right?
Right. If you throw a baseball at 1 meter per second from the center of the train toward the driver's cabin, and it's 10 meters away, it takes 10 seconds, the train's movement doesn't matter.
But light isn't a baseball. The author compares it to sound, I think, like an ambulance siren.
Yes. Imagine an ambulance and a runner are both moving down the street at 60% light speed. The ambulance blares its siren.
Sound moves at a constant speed through the air.
Exactly. So the sound, moving at a speed of 1, won't catch the runner in 10 seconds because the runner is actively moving away from the source of the sound.
The sound waves have to literally chase the runner down.
And that is exactly what light has to do in our moving train. The author visualizes firing 12 photon balls in a cone shape, pointing toward the driver's cabin at the front.
And because of those apparent speeds we talked about, the 0.8 on the z-axis and the 0.6 on the x-axis, the angle of that cone comes out to roughly 56.31 degrees.
Right. Now, if the train were truly stationary, standing at the platform, those photon balls would hit the back wall of the driver's cabin and leave a perfect circular trace.
And the radius of that perfect circle would be exactly 13.33 units.
But the train isn't stationary, it's moving at 0.6 c. So the light has to chase the driver's cabin at that sluggish apparent forward speed of 0.4 c.
Meaning the wall is running away from the light.
Yes. And the author runs the calculations in Blender. Now, they admit the math gets, quote, a bit suspicious or messy here, but the result is clear. It takes much longer for the light to hit the wall.
How much longer?
Around 25 or even 27.7 seconds, depending on the framing. And because it's taking so long to travel forward, the light has way more time to travel outward laterally.
Wait, so let me get this straight for the listener. The author is saying that if you shine a flashlight at the wall of a train moving near the speed of light, the circle of light on the wall will actually be larger and higher than if the train were standing still.
Exactly. The circle smears out. Instead of a radius of 13.33, you get a massive circular trace with a radius of 17.7 or even 22.16.
That is a massive distortion.
And if you fire a light ray at a 45-degree angle, it would hit even higher up the wall than expected. The train's forward movement delays the impact, so the light keeps traveling upward along the z-axis while it chases the wall.
It's just simple geometry catching up with us.
Yeah.
You absolutely cannot treat the inside of a moving vehicle as a closed, stationary system when mapping light.
You can't. The external movement physically warps the geometry of where the light lands. The light literally hits a different coordinate in 3D space than the equations say it should.
Okay, but if this geometry is so straightforward, if a 3D Blender file can just show us that the light lands in a different spot, why did the entire physics world adopt Einstein's relativity?
And this brings us to the trick mentioned in the author's title. The author argues that Hendrik Antoon Lorentz and Albert Einstein created a mathematical patch.
A patch, like a bug fix in a video game.
Pretty much. They created a patch to fix a fundamental oversight. And that oversight was treating a 3D finite space, like our train car, as having a simultaneous now.
Going back to the mathematical eye versus the camera eye.
Exactly. You cannot take a 3D Cartesian space and just use it as is when objects are moving through an electromagnetic field, because observation relies on light, and light takes time to travel.
So if the math wasn't working out because they ignored the delay of light, how did they patch it?
With Lorentz contraction, the idea that moving objects actually physically shrink in the direction they are moving.
All right, that's a huge pillar of relativity. If you go fast enough, your spaceship literally gets shorter.
Yeah.
But the author is saying that's just a math trick.
They are claiming it is entirely a mathematical trick. A Band-Aid used to make Minkowski spacetime diagrams work on paper, all because physicists completely ignored the apparent velocity of light.
Because they ignored that the light was only chasing the wall at 0.4 c.
Right. They looked at the math, saw the light didn't reach the wall when they expected it to, and instead of saying, oh, the light is delayed, they said, the wall must be closer. The train must have shrunk.
Oh, wow. So what does this all mean? We are talking about a massive claim here.
It is massive. The author calls it the ultimate fantasy. The idea that light is always at speed c relative to yourself in your own inertial frame.
The core rule of relativity.
Yes. The author believes that by tracking the delayed information from what physicists call the pass light cone, basically tracking the actual geometry of the light rays in Blender, they have unmasked the illusion of relativity.
That one of the fundamental pillars of modern physics is actually just a mathematical band-aid covering up a geometrical mistake about how we see light.
What's fascinating here is that the author isn't using new abstract equations to fight relativity. They are literally just using classical geometric visualization, a 3D rendering program, right, to challenge the abstract math of the 20th century.
It's like using a modern video game engine to prove Einstein wrong. That is a wild journey to take. I mean, we started with a simple 3D Blender cube.
A 20 by 20 by 20 box.
Right. And then we shifted from the absolute mathematical eye to the delayed camera eye. We put the train in motion at 60% the speed of light, threw some photon balls, and watched the geometry completely distort.
Leading to a direct challenge of Lorentz contraction. It's a lot to process.
It really is. It challenges this idea of a simultaneous now. And that actually leads to a really interesting kind of provocative thought for you, the listener, to mull over as we wrap up.
Yeah, think about this. The author argues that our physics might be flawed because we forget the delay of light reaching our camera eye. We forget that information takes time to cross space.
Even over tiny distances.
Exactly. So think about your own perception of the world. Everything you see, literally everything, even the device you are listening to this deep dive on right now, is technically in the past by the time the light reaches your retina or the sound hits your ears.
We are constantly living in a delayed projection.
We are. So if our entire perception of now is built on delayed projections, how much of our everyday human reality is an illusion? Think about your arguments with people, your sense of timing, your feeling of the present moment.
It's all just a perfectly constructed illusion based on delayed data.
How much of our reality is just a similar kind of patch we've built in our own minds to make the world make sense?
That is definitely something to think about. Thanks for joining us on this deep dive.